Okay, so in this video we're going to look at Bernoulli equations. The equation that you see in front of you here, dy dx plus px y equals qx y into y to the power n, is actually called the Bernoulli equation. You will notice that this is a first order ordinary differential equation and it is nonlinear. And the nonlinearity, of course, is because of this y to the power n. Now, of course, it will be nonlinear as long as n is not 0 or 1. And this nonlinearity in the power of y, this particular type of equation, as you see it, is known as a Bernoulli equation. So the substitution that usually works with such an equation is this one, v equals y to the power 1 minus n. It will transform the equation into a linear differential equation, and then one can solve it using the method of integrating factors, for instance. So let's have a look in detail how that works out to see what happens, how the equation actually transforms to a linear equation. So if we start by first differentiating this, then dv dx is just going to be 1 minus n y negative n here left, because subtract off the 1 times dy dx. Okay, so we've got that. Now what will happen is we need to basically from this rewrite so that we know what is dy dx, which is this, as you can see. Alright, just take these to the other side, and that tells us what dy dx is. Now we're ready to actually substitute it into the differential equation, and if we do that, we get this, right? And now, of course, what we'll do is, to simplify the equation, we'll multiply both sides by the reciprocal of this. So you can see here, I've left these so that you can see that actually this will go up and become 1 minus n over here, and these, of course, okay, will cancel out completely. So therefore the equation will become this. Now you have the dv dx there, 1 minus n as you see it, px, and then you're wondering, oh, where did the v come from? Well, if you see here, this, okay, is just going to be y to the 1 minus n, because the yn goes up, becomes this. And what is v from here? It's y to the 1 minus n. So we just replace that and we get this equation. Now what I want you to notice is, remember, n is just a number, okay, and so we have basically come to linearize the equation. So this is now a linear differential equation, first order, okay, and we are now able to, in fact, solve this equation using the method for linear first order ordinary differential equations. So let's look at an actual example. You might recall we did this equation in the previous video where we were using the substitution x over y. So the y over x, sorry. So we divided this by xy and continued further. Let's look at it from another angle now. We can rewrite it as following: dy dx minus 3 over 2x times y equals 2x over y. That results in the same division by 2xy as we did in the previous video. But instead of keeping this on this side, we bring it on towards this side. And what happens is, now you can compare, okay, you can compare these here by looking at, for instance, this term here, okay. So if we look at these terms, basically what you have is this, it comes up and becomes y to the minus 1, and that makes this a Bernoulli equation, in fact, with n equal to minus 1. So this is a Bernoulli equation with n equals minus 1, okay, because here I'll show you. So I could just rewrite this as dy dx minus 3 over 2x y equals 2x into y to the minus 1. Okay, so this, okay, is your q x, and this over here is the function px, that is this q, this p and q. And you can see here the yn is y to the minus 1, so therefore we end up with n equals minus 1. That's important because that tells us that our substitution that should work is v equals to the 1 plus 1. Okay, so it's equal to y squared. So that substitution should work. Now, it is a good idea not to memorize, this equation here. Personally, I would. So we get basically 1 over 2y dv dx minus 3 over 2xy equals 2x over y. So then multiply both sides by this 2y term here, so we can get our dv dx with a coefficient of 1, and as that goes over here, it just becomes 3 over x y squared. The 2 cancels, okay, and it's equal to, over here you're going to have the just 4x, okay, and the y is gone. So we end up with this equation, and you're still thinking, oh wait, what about that y squared? We can't have y, v, and x all together. So of course you can clearly see that y squared is v, so it just becomes this differential equation. And you can clearly see now this is a linear differential equation, and we can use a method like integrating factor with your p being minus 3 over x, and the integrating factor will be just x to the minus 3 in this case. So here I've just shown you, so the integrating factor rho is just x to the minus 3, and then it's quite easy to solve it. So here you'll see basically the derivative of that is equal to this, so that's just going to be then x minus 3v equals the integral of 4x to the minus 2 dx. Very easy to finish. So just for completion, I've shown it here. There we've got the solution, and it's done. So that is a typical example of a Bernoulli equation. And in this video, what we've done is we started by looking at what it looks like, and then how a simple substitution can actually convert the Bernoulli equation to a linear one, and a method of integrating factor can be used to solve that equation. So that's basically it. So this is another example, as you can see here. I will leave this to you for a quick exercise to see if you can follow and do this question. And of course, I would give you a hint that remember that to compare this to a Bernoulli equation, all right, there's our Bernoulli equation. Remember, dy dx must have a coefficient 1, so you will divide by x first and then proceed and see, do you have an n that is not 0 and not 1, and then you proceed with the substitution. Hopefully you get the idea, and let me know if you have problems with this question. Thank you so much.